and the transition from the physical endurance of superalloys to the operational reality of rapid reusability requires a fundamental shift in how we define maintenance. In the legacy era of spaceflight, an engine was a silent partner. It provided thrust, and if it survived the mission, it was poked, prodded, and disassembled by a small army of technicians to determine if it could fly again. This was a reactive, manual, and incredibly slow process, the antithesis of the airline model. And to bridge this gap, the Raptor 3 has been designed as a self-reporting node within a larger distributed network. It is no longer a dumb assembly of valves and chambers, but a sophisticated hardware-software stack. If the structural integrity of the engine is its body, then the integrated sensor suite and the flight computer represent its nervous system and brain. For the computer scientist, the Raptor 3 does not just run a mission. It executes a continuous integration suite in real time, where the code being tested is the physical state of the hardware itself. In the hardware unit test, pre-flight and in-situ diagnostics. In software engineering, a unit test is a script designed to verify that a specific module of code performs exactly as expected under a set of defined inputs. For the Raptor 3, every ignition sequence begins with a series of physical unit tests. And before a single drop of propellant enters the combustion chamber, the engine's controller, a redundant, high-performance computing cluster mounted directly to the engine, executes a sub-millisecond sweep of every integrated sensor. This is the static analysis phase. The system checks for null pointers in the hardware, a pressure transducer returning an out-of-range value, a temperature sensor showing an impossible gradient, or a valve actuator drawing too much current, which is a sign of mechanical resistance or bit rot in the hardware. And once the pre-burners ignite, the unit testing moves from static to dynamic. The engine enters a high-fidelity feedback loop where the software monitors the latency between a command such as increase oxygen flow by 5% and the physical response measured in chamber pressure. If the hardware responds too slowly, it indicates a bottleneck in the system, perhaps a clogging injector or a sluggish turbopump. In a disposable architecture, you might ignore a 10-millisecond lag. In a reusable architecture, that lag is a failing test case that triggers an immediate abort or a flag for post-flight inspection. And the digital twin, real-time shadowing, and telemetry comparison. The most advanced aspect of the Raptor 3 health management is the implementation of the digital twin. This is not merely a 3D model. It is a high-fidelity, physics-based simulation of the engine that runs in parallel with the physical hardware during the flight. And think of this as a shadow mode deployment, common in autonomous vehicle testing. As the physical Raptor 3 burns through the atmosphere, the digital twin calculates what the ideal engine should be experiencing at that exact altitude, throttle setting, and propellant temperature. The physical reality, the engine reports a turbopump vibration of 14.2 kHz. The digital twin, based on the current flow rates and pressures, the simulation predicts a vibration of 14.1 kHz. The delta, the 0.1 kHz difference, is the anomaly. And by comparing real-time telemetry against the Gold Master simulation, the Raptor 3 can detect subtle deviations that would be invisible to a human observer. This is the hardware equivalent of log analysis. In a massive distributed system like a web server cluster, you look for spikes in 500-level errors or increases in CPU steal time. On the Raptor 3, the software looks for spectral drift, subtle shifts in the frequency of mechanical vibrations that suggest a bearing is wearing down or a fatigue crack is altering the resonant frequency of a manifold. And this predictive maintenance model allows SpaceX to move away from time-based maintenance, involving replacing a part every 10 flights, toward condition-based maintenance, where you replace a part only when the data proves it is nearing failure. This is the key to the $10 million per flight goal of Starship. You do not waste resources fixing what is not broken, but you never fly a component that the data has deprecated. And software-defined reliability, handling hardware exceptions. In a standard C++ or Rust environment, an exception is an event that disrupts the normal flow of instructions. The programmer writes try-catch blocks to handle these events gracefully. The Raptor 3 flight software is essentially a massive, real-time try-catch block for the laws of physics. And consider a hard start, where the timing between the spark and the propellant flow is off by a fraction of a second, causing a pressure spike. In the 20th century, this often resulted in the kernel panic of rocketry, an engine explosion. The Raptor 3, however, uses its integrated sensor suite to catch the exception. And if the internal pressure sensors detect a spike exceeding the safe mode threshold, the software can execute a graceful degradation routine. It might instantly throttle down to relieve structural tension, or adjust the mixture ratio to cool the chamber, sacrificing a bit of efficiency to preserve the hardware integrity. This is analogous to a modern CPU thermal throttling. When it hits 100 degrees Celsius, the system slows down to prevent a permanent hardware crash. And this software-defined reliability means that the engine is self-aware. It knows its own error logs. After a landing, the engine does not just sit there. It uploads a system report to the SpaceX ground servers. This report is not just a dump of raw data. It is a summarized health score. Using machine learning models trained on thousands of previous test stands and flight hours, the ground software analyzes the difference between the engine's state before and after the flight. If the unit tests pass and the health score remains above the threshold, the engine is cleared for immediate refueling, no human intervention required. And integrated sensors and the observer affect the shift from the spaghetti of external sensors seen on Raptor 1 to the integrated sensors of Raptor 3 is more than a mechanical improvement. It is a breakthrough in observability. In software, observability is the measure of how well you can understand the internal state of a system from the external outputs it provides. And older engines were black boxes. You knew the pressure at the inlet and the pressure at the outlet, but the middle was a mystery. You had to infer what was happening inside. The Raptor 3 printed body contains internal taps and sensor ports that are part of the monolithic structure. This allows for deep instrumentation. And we are now monitoring the internal state of the metal itself. By embedding sensors closer to the critical sections, the areas of highest heat and pressure, SpaceX has eliminated the noise associated with external mounting. In data science terms, the signal-to-noise ratio of Raptor 3 telemetry is orders of magnitude higher than any previous rocket engine. This high-fidelity data is what makes the digital twin possible. You cannot build a high-accuracy model if your input data is jittery or lossy. And the garbage collection of physical systems. Even with the best software-defined reliability, physical systems still accumulate technical debt. In a long-running software process, garbage collection is the process of reclaiming memory that is no longer being used. In the Raptor 3, garbage collection is the process of identifying and managing the physical degradation that cannot be coded away. And, as we discussed in the previous section, every thermal cycle allocates a bit of the engine's fatigue life. The software tracks this allocation. It keeps a running tally of total seconds at max throttle and total thermal shock events. When the fatigue memory of a specific component, say, the oxygen turbopump, reaches a certain percentage of its total bytes written equivalent, the system marks that component for collection. And this is where the automated health check becomes a logistics engine. The software doesn't just say this part is broken. It says this part will likely fail in 12 more cycles. Schedule a swap out after the next mission. This allows SpaceX to treat engine maintenance like a background process in an operating system. It happens quietly, predictably, and without halting the main thread of launch operations. And from fragile to antifragile, the ultimate goal of the Raptor 3 digital nervous system is to move the engine from being robust to being antifragile. A robust system resists stress. An antifragile system gets better with more data. And every time a Raptor 3 flies and generates a system report, that data is fed back into the global model. If engine number 142 experiences a unique vibration pattern during a landing in high winds, every other Raptor 3 in the fleet learns from that event. The digital twin is updated, the unit tests are refined, and the safety margins are adjusted across the entire fleet. And this is the hardware-software stack in its final form. The Raptor 3 is not a static piece of hardware. It is a versioned system. The engine you fly today is version 3.4.1, and by the time it lands, the data it gathered has already contributed to the version 3.4.2 flight software update. This continuous loop of flight leads to data, leads to analysis, leads to optimization, is what allows SpaceX to achieve the rapid turnaround necessary for Mars. And in the 20th century, a rocket engine was a work of art, unique, temperamental, and fragile. In the 21st century, the Raptor 3 is a containerized service. It is designed to be swapped in and out, monitored by automated scripts, and run until its service level agreement is met. And the convergence of body and brain. We have explored the body of the Raptor 3, the superalloys, the 3D printed channels, and the monolithic architecture that resists the violent fatigue of spaceflight. And we have now explored the brain, the software, the digital twins, and the automated health checks that ensure the body is performing within its parameters. And but a single engine, no matter how smart or durable, cannot lift the largest object ever built by man. The true power of the Raptor 3 is not found in its individual performance, but in its ability to work as part of a massive, synchronized collective. To launch the Starship system, we must move from the unit testing of a single engine to the system orchestration of dozens. And the complexity of managing one Raptor 3 is a challenge of engineering. The complexity of managing 33 of them simultaneously is a challenge of choreography. This orchestration, the delicate balance of power, vibration, and timing required to lift the super heavy booster, is the final hurdle in the quest for the stars. And this leads us to the final chapter of our journey, where we see the Raptor 3 not as a solo performer, but as a member of the most powerful orchestra in human history, 10.133 Raptors, the choreography of the super heavy booster.